All right, welcome back. Part 2 of probability applications. So here goes. You select 5 cards from a standard deck of 52 cards. Find the probability that, okay? And we're going to ask you 3 questions here. So we're going to start with this first one. All 5 cards are face cards. So what do we know? There's a couple of ways to do this. I'm going to use the fundamental counting principle, okay? So what do we know? We're going to pick 5 cards. So let's look at the bottom. Let's look at our total number of possible outcomes. Total number of possible outcomes. So for my first card, how many choices do I have? The answer is 52. For my second card, I have 51 choices. For my third card, I have 50. For my fourth card, I have 49. And for my fifth card, I have 48. Okay? So that would be my total number of possible outcomes. Now, the top is what fits this description. Okay, so they want all 5 cards to be face cards, and they specify a jack, a queen, and a king. Okay, so there are 4 jacks, 4 queens, and 4 kings. So there are 12 cards that satisfy this description. So for my first choice, I have 12 ways to meet this criteria. For my second card, I have 11 ways to meet this criteria. For my third, I have 10. For my fourth, I have 9. And for my fifth, I have 8 ways to meet this criteria. And then it's a simple question of multiplying these out and getting the answer. So 12 times 11 times 10 times 9 times 8, and that's going to give me 95,040 ways of drawing 5 face cards. And then we're going to do the bottom number, 52 times 51 times 50 times 49 times 48, and that's going to give me 311,875,200. Okay? And then you have to ask the question, are they going to ask me for fraction? Are they going to ask me for decimal? If they ask for a decimal, you simply divide these. If they ask for a fraction, you're going to have to reduce them. And so let me see if I can do that real quick, because I think this does actually reduce. And it does. It reduces to, let me see if I can squeeze this in here, 33 over 108, 290. Okay, 108, 290. So if they ask for a fraction, that's your answer. If they ask for a decimal, you would simply divide these and round to whatever place they ask for. Okay, so question 2. This time you get 3 aces and 2 kings. Now, I'm going to cheat. I know the bottom number is that 311,875,200. Why? Because I'm still drawing 5 cards. The first card's still going to be 52 choices. The second's going to be 51. The third's going to be 50. That bottom number doesn't change, so I can just jot it down. So then it's 3 aces and 2 kings. So let's start with how many aces are in the deck? 4. So my first draw, I have 4 aces to pick from. My second draw, there's 1 gone because it's in my hand. That leaves 3 aces to pick from. My third draw, I have 2 in my hand. That leaves 2 aces to pick from. Okay, boom, boom, boom. So there's my first draw, second draw, third draw. Ace, ace, ace. Now what? I need what? Kings. So for my fourth draw, there are 4 kings in the deck. 1 ends up in my hand. So for my last draw, there are 3 kings in the deck. So that top number, 4 times 3 times 2 times 4 times 3, is 288. So I end up with 288 over that 311,875,200 number. Okay? Now we reduce that, right? So that's going to be over 311,875,200. And that reduces to 1 over 108. I think I missed a 0 here. That's 1082900. Okay, that should be right. That looks good. Okay, so there's our answer to that one. And then part C. Part C is another trick question. Why? How many queens I'm going to ask you, what's the probability you get 5 queens? There are only 4 queens in the deck. So what does that mean? This is impossible. So therefore, the probability equals 0. Probability is 0. You can't draw 5 queens. Unless, of course, you're cheating, right? Okay, so a box contains 30 light bulbs, and we know 5 of them are blown. We don't know which 5. So you have 30 light bulbs in a box, 25 are good, 5 of them don't work. You're going to pick 5 random light bulbs out of this box, and we want to know what's the probability that all 5 are defective, all 5 are blown. Again, probability, so we immediately know it's going to be a fraction. Okay, let's look at our total number of outcomes. There are 30 light bulbs in the box, so my first choice is going to be what? 30 bulbs. Okay, I draw a bulb. Now how many are in the box? 29. So the second choice, I'm going to have 29 choices. When I go back to the box, there are going to be 28 choices. When I go back to the box, there'll be 27 choices. And when I go back one more time, there'll be 26 choices. Okay? So boom, 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 boom. Your bottom number will be 30 times 29 times 28 times 27 times 26. Okay. Now, how about the top? What are we picking from? We're not picking from all light bulbs. We're only picking from what? The defective light bulbs, the blown light bulbs. Okay? So, my first choice, how many blown light bulbs are there? There are 5. When I go back to the box, my second choice, there are 4. When I go back to the box, my third choice, there are only 3 blown light bulbs. When I go back to the box to pick my 4th light bulb, there are only 2 blown light bulbs. And then, of course, when I go back to the box to pick my last light bulb, there's only 1 blown light bulb. So we have 5 times 4 times 3 times 2 times 1, and that's going to be 120 on top. You can skip the times 1. 30 times 29 times 28 times 27 times 26 on the bottom, and that's going to be 171,00720. So that's going to be something like 17,100,720. And then, of course, for our homework, they are going to ask us to reduce this fraction. So it's going to be 120 over that answer, and that reduces to 1 over 142,506. Okay? So that's our probability of drawing 5 blown light bulbs out of a box of 30 that have 5 blown light bulbs. Okay? So it's a pretty slim chance, isn't it? Okay, that's a good thing. Now, what's the probability that we pick 5 light bulbs and none are defective? Okay, so let's work this one out. Now, what do we know about the bottom number? The bottom number is going to be that same 17,100,720. Okay, the top number, there are 30 total light bulbs. 5 of them are defective. That means if I'm picking from the pile that are not blown, I have 25 choices for my first selection. And for my second selection, I'll have 24. For my third selection, I'll have 23. For my fourth selection, I'll have 22. And for my last selection, right, 1, 2, 3, 4, 5 light bulbs picked. Okay? So now we got to figure out what's 25 times 24 times 23 times 22 times 21. We spent a lot of time multiplying in this class. And we get 6375600. Okay, so 6,375,600 divided by that 17,100,720. So let's do the math. And if they want this as a fractional answer, it will give us 1265 over 3393. Okay? So, there's our probability. If you turn that into a decimal, it's about 37%. So this is about a 37% chance that you can pick 5 light bulbs and not pick a blown one from this box. That's pretty good. I'd like it to be higher, but that's pretty good. Okay? Now, part C says 1 of the chosen bulbs is defective. So we're going to pick 5 bulbs, and we're saying 1 is defective and 4 are not defective. So we have to pick 1 bad one and 4 good ones. 1 bad one and 4 good ones. So we're going to have 2 different things going on in our numerator. So what do we know about our denominator? We know our denominator is going to be 17,100,720. Why? Because you got 30 times 29 times 28 times 27 times 26. Now, we're going to start with our 1 defective bulb. How many choices do I have for that defective bulb? I have 5 choices for my defective bulb. Okay? Now, the other 4 are not defective. So when I go back in, my first how many choices do I have for my next pick? It'll be 25. Then 24, then 23, and then 22. Right? So 1, 2, 3, 4 good bulbs, 1 bad bulb. Why? Because there are 5 bad bulbs to pick from. Here there are 25 good bulbs. Well, because I picked 1, now there are only 24. Then because I picked 1, there are only 23. Then because I picked 1, there are only 22. Okay, so we're going to multiply these all out. 5 times 25 times 24 times 23 times 22. And that's going to give me 1,518,000 over our 17,100,720. And then we're going to reduce this fraction. And we're going to get 6375 over 7,1,253. Okay? And if I turn that into a percentage, it's about a 9% chance. So you have about a 9% chance of selecting 1 defective bulb out of 5. Okay? So anyway, and then of course I might ask a follow-up question in class that says, which of these has the highest probability? And the easiest way to tell that's to turn all of these into decimals. And this one would be the highest probability. I think I said it was 30-some percent. Let's see if I can find that answer on my calculator. Nope. Okay. So, anyway, let's do one more. 6 people are slated to speak at an event. Person A, B, C, D, and F. And we want to find the probability that person A goes last. We want to find the probability that person C goes first and A goes second. And then we want to find the probability that the speakers go in the exact order B, A, D, F, E, C. Okay? So we're going to do part A first. Okay? Part A first. So, here's the deal, guys. Let's start with the denominator. We have 6 people, and we have to know how many ways they can speak. How many ways can you pick 6 people? So, I'm going to start with, when we pick our first speaker, we have 6 choices. When we pick our second speaker, we have 5 choices. When we pick our third speaker, we have 4 choices, on and on and on. And when we pick our last speaker, we have 1 choice. There's your bottom number. Okay? Let's go ahead and find that out. So our bottom number will be 720. The fun part is it'll be the same number for B and C, so we have half those problems done. Now, part A says person A has to go last. So, here we go. When I go here, I'm going to start here. How many choices do I have for my last spot? I have 1 choice for my last spot. Why? Person A has to go in that spot. So we do that first. He's last. Okay? Person A goes last. Now, if person A is last, how many choices do I have for my first spot? It's going to be 5. Why? Because person A is already out of the mix. Person A is last. I have 5 choices for that first spot. Then what? I'll have 4 choices for the second spot, 3 choices for the third spot, 2 choices for the fourth spot, and 1 choice for the fifth spot. Okay? And then person A goes last. And you can go ahead and multiply those out. And so that'll be 5 times 4 times 3 times 2 times 1 and times 1 again. And that'll be 120. And then, of course, if they want us to reduce that, that would reduce to 1 out of 6. There is a 1 in 6 chance that person A goes last. That actually makes sense to me because there's a 1/6 chance that person A goes last. There's a 1/6 chance that person B goes last. There's a 1/6 chance that person C goes last because there are 6 people. Okay? So, part B. Let's do part B. So I'm going to do part B right here. It says person C goes first, person A goes second. Okay, so let's break this down. It's a probability question, so it's going to be a fraction. We know the bottom number is going to be 720 because we already took care of that. Now, person C goes first. So for my first choice, I have 1. For my first selection, I have 1 choice. It has to be person C. For my second selection, I have 1 choice. It has to be speaker A. Now, let's fill in. How many people are left to pick for my third speaker? I have 4 choices for my third speaker. I have 3 choices for my fourth speaker, 2 choices for my fifth speaker, and 1 choice for my sixth speaker. So it'll be 4 times 3 times 2 times 1 times 1 times 1, which is 24 over 720. And then if I reduce this fraction, I get 1 over 30. 1 over 30. That's my probability that person C goes first and person A goes second. Okay? And again, using the fundamental counting principle, we have 1 choice for first, we have 1 choice for second, and then there's 4 people left, so 4, 3, 2, 1. Okay? So if you understood that, then part C we'll do down here. Part C, the speakers go in this exact order, B, A, D, F, E, C. Okay, so, ta-da, the bottom number has to be 720. How many choices do I have for my first slot? I have 1 choice. How many choices do I have for my second slot? I have 1 choice. How many choices do I have for my third slot? I have 1 choice. You get the idea. It's 1 times 1 times. Why? Because we have 1 choice for each slot, so we get 1 over 720. Okay? That they go in that exact order. So anyway, these are probability applications. These are the types of problems you would see in a quantitative literacy or survey of math book in probability, but you might also see these in a statistics textbook. So anyway, probability applications, make sure you know the fundamental counting principle, combinations, and permutations. And just as a side note, these last 3 examples, I used the fundamental counting principle on all 3 of them. But you may also use other counting techniques. I prefer the fundamental counting principle when it comes to these types of problems because it makes more sense to me and I think it's easier to explain. But just know that you can use permutations or combinations if the rules are met that there are no repeats and whether the order matters or not. Okay? So anyway, that is probability applications. Please leave any questions you have in the comments or email me and I'll be glad to answer them.